Hallo, guten Morgen. Schön, dass Sie da sind.
Ja, gerne, gerne.
Good morning, ladies and gentlemen. I would like to welcome you all here for our symposium, Challenges in Robotics, Down to Earth at the German Aerospace Center.
Ladies and gentlemen, dear Professor Hürzinger, Mrs. Hürzinger, I'm very pleased and honored that I'm able to open this symposium because, of course, Professor Hürzinger is one of our institute directors who are really changing the world, but at the same time doing all the best for DLR. Stay hungry, stay foolish, and I think this is describing how you are working for the whole time, and I wish that you're going on with that.
Ladies and gentlemen, besides infrastructure, a very decisive factor for excellent research is also international exchange. I am therefore delighted that today and tomorrow the DLR Institute of Robotics and Mechatronics is acting as a host to the elite from all over the world in the field of robotics.
You are all so important for us, and I'm so happy to see so many of my robot research colleagues as well as representatives of companies. And okay, here you can see the effect. If a robot on a satellite reaches out and comes back in the same way, the satellite is in the same position again. If it moves out and comes back in another way, then you can reorient the satellite. And down here you could see that a gripper may make the same motion, but when the joints of a redundant robot are moving differently, then the satellite is also reoriented in a different way. So our plans are to use this kind of effects maybe with high torque reaction wheels, not with an arm really.
So here is one extreme, taking the human to interact with the simulation, and the simulation now is performing what the human task is while maintaining the different constraints, and the human is grasping a virtual object and now it's letting go, and yeah, I made it without falling.
So I wanted to pay attention in particular to these two squares, this black A tile and this white B tile. So this shows you how amazing our perception is, because the two tiles are exactly the same color. You wouldn't believe that, right? I mean, I didn't believe it. I looked at that. No way.
Another is that you put multiple of these together in order to form a multi-wheeled vehicle. And so I'm going to show a movie of our efforts with this dual-axle concept where we can provide that kind of capability. And I'm going to skip ahead. So here you see the axle system driving over fairly rough terrain. That slope is probably about 30 degrees.
So I borrowed this picture from Usama. I have to say that it's the second time in my life I see Usama wearing a tie, and I was kind of impressed this morning. So this must be really an important event, and I'm flattered to be here.
This is one robot which is built with magnetic wheels, but if you have magnetic wheels, you have also to need these very small wheelets to get rid of the magnetic force if you go around corner. And this is a robot which is extremely flat. It's about less than a centimeter in thickness, which is intended to do inspection between in a generator between the motor, the rotor and the stator.
And the KUKA Titan was introduced 2007 with a payload of 1,000 kilogram, at that time holding the world record with a reach of 3.2 meters, a mass of 4.6 ton, and a repeatability on 0.2 millimeter in the overall range, based on methods which we have been taught and acquired at the DLR.
Performance of the new Ashmo, which is announced and opened 2 weeks ago. This is just jumping, one leg and 2 legs, and so on. So it means the progress on the servo system becomes very good. And the speed of the running, 9 kilometers per hour, very good speed. And also, they also kicked the ball. Maybe Justin will grab it, the goalkeeper, I think.
So far, we have built several prototypes of the musculoskeletal humanoid like this. This is the current Kojiro, the 5th version. It has a non-linear spring antagonistic structure inside the wrist, then it can impact motion like this. But you see, the human can play like this. So we have to build another ideas to reach this way.
So to understand how it works, how the model works, you can think of the inner representation of the hand going within the object, but the outer representation, the real hand, being compliantly connected to this set point and being repelled by the object, which will take the hand out of the object. And the repulsion forces will grab the object. So does this mean anything? Well, this is a nice, I think, visualization. So you have the virtual hand, that is the inner projection of the hand, that is controlled on this synergy manifold and moves according to this manifold. But the real hand will stop on the object and act forces on the object that are proportional to the displacements.
Yeah, I know that when most people know me, know that I'm never done much work in humanoids. And I always said I can't find an application. I have an application, finally. And this is actually what we're doing with the Australian Institute of Sport. We're helping train athletes for the next Olympics. And what it is, we've captured all the motion of the swimmers, and we have a full computational fluid dynamics environment of the water. And actually, you can actually analyze how the swimmers swim. And using the work of my colleagues in the humanoid area, we've been able to actually control the swimmer to see if they change the stroke, can they actually go faster, so the coach can actually coach.
Now, I actually, in the 90s, I guess kind of moving ahead a decade, did a lot of work in real-time vision. And again, this is an example of something that we really probably could not have done the decade earlier, simply because we didn't have the computing power. Once we had the computing power, it became very interesting to start to invent algorithms that could solve very interesting types of problems. You know, starting with simple face tracking, then going to multi-cue tracking, in this case using a particle filter, which was the next iteration on the Kalman filter. And then tracking in clutter, actually using some machine learning ideas, and tracking very high degree of freedom systems.
In order to understand an action performed by someone else, or to anticipate the goal of the action, we are using the part of the brain which is involved in the execution of that action. So there is no more a bodiless interpreter. It has to have a body, or at least a knowledge about body movement. And I have a very simple, just presenting just one result of an experiment that was done by a group in Rome, just to show that the better I am in acting, the better I am in understanding. And what these people did was to show video clips, like the one that I'm going to show here. You know, a person shooting a ball into the basket. And the question was, is the ball going into the basket or not? Okay, so simple ballistic movements, you know, in some sense, but they made it difficult, you know. Instead of just showing the whole movement or a big part of the movement, they started by showing just half a second of the movement, you know, of the shooting. And what they discovered is that for professional basketball players, they are very good. They can tell you above chance if the ball is going inside or not.
So this is, for example, one example, a benchmark in the kitchen, loading the dishwasher, deloading the dishwasher, making the dish, and everything is done with a control loop. It has been demonstrated, mapped, and then to make the robot to do it. Here's one example where the question is, what is this? This is a spoken dialogue, this is a book. But the robot is not able to read the book. It's a book on control theory. And so you can ask, what is this? The robot says, this is a book, but you don't know what is inside. So this is some of the problems where semantics are necessary to understand what to do with this and maybe for what it's useful for.
But I mentioned that things are moving faster. I wrote here something miraculous happened within this morning. The story is the following. After the visitors have been away yesterday and during the night, I cannot explain it in a different way. Justin felt alone, felt lonesome, and he moved out of his hall, went into the central entrance hall and saw the hand-arm system, we are calling it Hasi. So it's still throwing balls. And he asked the Hasi, hey, you're also alone now, can't we play together? What do you think about that? Hasi answered, yeah, this might be a good idea. And apparently they did it. And this, and this was really not planned before, because in the past we sometimes had problems in calibrating the system. For example, just in the hand-eye calibration took some time. Now things are going much, much faster. And so it's not a big generalization, but there's a different ball. Justin has always had these big white balls. Now this is a smaller red ball. Small changes, but nevertheless that it worked immediately shows that we are moving forward faster. And of course, I'm very happy about that. Thank you very much. Thank you. Thank you. Thank you very much.